Colossus was the name of a series of computers developed by British codebreakers in 1943 to 1945 to help in the cryptanalysis of the Lorenz cipher. Colossus used thermionic valves and thyratrons to perform Boolean and counting operations. Colossus is thus regarded as the world's first programmable, electronic, digital computer, although it was programmed by plugs and switches and not by a stored program. Colossus was designed by the engineer Tommy Flowers to solve a problem posed by mathematician Max Newman at the Government Code and Cipher School at Bletchley Park. Alan Turing's use of probability in cryptanalysis contributed to its design. It has sometimes been erroneously stated that Turing designed Colossus to aid the cryptanalysis of the Enigma. Turing's machine that helped decode Enigma was the electromechanical bomb, not Colossus. The prototype, Colossus Mark Chapter 1, was shown to be working in December 1943 and was operational at Bletchley Park on 5 February 1944. An improved Colossus Mark Chapter 2 that used shift registers to quintuple the processing speed first worked on 1 June 1944, just in time for the Normandy landings on D-Day. 10 colossi were in use by the end of the war and an 11th was being commissioned. Bletchley Park's use of these machines allowed the Allies to obtain a vast amount of high-level military intelligence from radiotelegraphy messages between the German High Command and their army commands throughout occupied Europe. The destruction of the Colossus hardware and blueprints, as part of the effort to maintain a project secrecy that was kept up into the 1970s, deprived most of those involved with Colossus of credit for their pioneering advancements in electronic digital computing during their lifetimes. A functioning replica of a Colossus computer was completed in 2007 and is on display at the National Museum of Computing at Bletchley Park. Purpose and origins. The Colossus computers were used to help decipher radio teleprinter messages that had been encrypted using an unknown device. The British called encrypted German teleprinter traffic fish, and the unknown machine and its intercepting messages tunny, before the Germans increased the security of their operating procedures. British cryptanalysts diagnosed how the machine functioned and built a machine that emulated it. It was deduced that the machine had 12 wheels and used a Vernam ciphering technique on message characters in the standard 5-bit ITA2 code. It did this by combining the plain text characters with a stream of key characters using the XOR Boolean function to produce the ciphertext. In August 1941, an operating blunder led to the transmission of two versions of the same message with identical machine settings. These were intercepted and worked on at Bletchley Park. First, John Tiltman, a very talented GC and CS cryptanalyst, derived a key stream of almost 4,000 characters. Then Bill Tutt, a newly arrived member of the research section, used this key stream to work out the logical structure of the Lorenz machine. He deduced that the 12 wheels consisted of two groups of 5, which he named the chi and psi wheels. The remaining two he called mu or motor wheels. The chi wheels stepped regularly with each letter that was encrypted, while the psi wheels stepped irregularly, under the control of the motor wheels. With a truly random key stream, a Vernam cipher removes the natural language property of a plain text message of having an uneven frequency distribution of the different characters, to produce a uniform distribution in the ciphertext. The tunny machine worked well in this respect, but the cryptanalysts worked out that examining the character-to-character changes of character streams, instead of the frequency distribution of ciphertext characters, showed a departure from uniformity which provided a way into the system. This was achieved by differencing, in which each bit or character was XORed with its successor. In order to decrypt the transmitted messages, two tasks that had to be performed. The first was wheel breaking, which was the discovery of the CAM patterns for all the wheels. These patterns were set up on the Lorenz machine and then used for a fixed period of time for a succession of different messages. Each message was enciphered with a different start position of the wheels. Alan Turing invented a method of wheel breaking that became known as Turingery. Turing's technique was further developed into rectangling, for which Colossus could produce tables for manual analysis. Colossi 2, 4, 6, 7 and 9 had a gadget to aid this process. The second task was wheel setting, which worked out the start positions of the wheels for a particular message, and could only be attempted once the CAM patterns were known. Colossus was initially designed to discover the start position of the Chi wheels for a message, not for completely decrypting it. To do this, it compared two character streams, counting statistics based on a succession of programmable Boolean functions. The ciphertext was read at high speed from a paper tape. The key stream was generated internally, in a simulation of the Lorenz machine. Decryption processes. By using differencing and knowing that the psi wheels did not advance with each character, Tut worked out that trying just two differenced bits of the Chi stream against the differenced ciphertext would produce a statistic that was non-random. This became known as Tut's 1 plus 2 break-in. It involved calculating the following function: increment z1, increment z2, increment 1, increment 2, increment 1, increment 2, and counting the number of times it yielded false. If this number exceeded a defined threshold value known as the set total, it was printed out. The cryptanalyst would examine the printout to determine which of the putative start positions was most likely to be the correct one. This technique could be applied to any pair of impulses, and so provided the basis of an automated iterative approach to obtaining the decay of a ciphertext, from which the psi component could be removed by manual methods. If the frequency distribution of characters in the decay version of the ciphertext was within certain bounds, wheel setting of the Chi wheels had been achieved, and the message settings and decay could be passed to the test tree. This was a section at Bletchley Park led by Major Ralph Tester, where the bulk of the decrypting work was done by manual and linguistic methods. Design and construction. Colossus was developed for the Newmanry, the section headed by the mathematician Max Newman that was responsible for machine methods against the Lorenz machine. The Colossus design arose out of a prior project that produced a counting machine dubbed Heath-Robinson. The main problems with Heath-Robinson were the relative slowness of electromechanical parts and the difficulty of synchronizing two paper tapes, one punched with the enciphered message, and the other representing the key stream of the Lorenz machine. Heath-Robinson tapes tended to stretch when being read, at some 2,000 characters per second, resulting in unreliable answers. Tommy Flowers was a senior electrical engineer and head of the switching group at the Post Office Research Station at Dollis Hill, who had been appointed MBE in June 1943. Prior to his work on Colossus, he had been involved with GC and CS at Bletchley Park from February 1941 in an attempt to improve the bombers that were used in the cryptanalysis of the German Enigma cipher machine. He was recommended to Max Newman by Alan Turing, who had been impressed by his work on the bombers. The main components of Colossus's predecessor, Heath-Robinson, were as follows: a tape transport and reading mechanism that ran the loop key and message tapes at between 1,000 and 2,000 characters per second, a combining unit that implemented the logic of Tut's method, a counting unit that had been designed by Dr. C. Wynne Williams of the Telecommunications Research Establishment at Malvern, which counted the number of times the logical function returned a specified truth value. Flowers had been brought in to design the Heath-Robinson's combining unit. He was not impressed by the system of a key tape that had to be kept synchronized with the message tape, and, on his own initiative, he designed an electronic machine which eliminated the need for the key tape by having an electronic analog of the Lorenz machine. He presented this design to Max Newman in February 1943, but the idea that the 1 to 2000 thermionic valves proposed could work together reliably was greeted with great skepticism, so more Robinsons were ordered from Dollis Hill. Flowers, however, knew from his pre-war work that most thermionic valve failures occurred as a result of the thermal stresses at power-up, so not powering a machine down reduced failure rates very substantially. Flowers persisted with the idea and obtained support from the director of the research station, W. Gordon Radley. Flowers and his team of some 50 people in the switching group spent 11 months from early February 1943 designing and building a machine that dispensed with the second tape of the Heath Robinson by generating the wheel patterns electronically. This prototype, marked Chapter 1 Colossus, performed satisfactorily at Dollis Hill on 8 December 1943 and was taken apart and shipped to Bletchley Park, where it was delivered on 18 January and reassembled by Harry Fensom and Don Horwood. It attacked its first message on 5 February 1944. As it was a large structure, it was quickly dubbed Colossus by the WRNS operators. This machine contained 1,600 thermionic valves, and was soon followed by an improved production marked Chapter 2 machine. 9 of this version of the machine were constructed, the first being commissioned on 1 June 1944, after which Alan Coombs took over leadership of Colossus production. The original marked Chapter 1 machine was converted into a marked Chapter 2, and an 11th Colossus was essentially finished when the war in Europe ended. The main units of Flowers' design were as follows: a tape transport and photoelectric reading mechanism very similar to Heath Robinson's, a coder and adder that simulated the Lorenz machine using thyrotron rings, a logic unit that performed Boolean operations, a master control that contained the electronic counters, a printer. Most of the design of the electronics was the work of Tommy Flowers, assisted by William Chandler, with Sidney Broadhurst working on the auxiliary electromechanical parts. The marked Chapter 2 Colossus was designed while marked Chapter 1 was being constructed. It contained 2,400 valves and was both 5 times faster and simpler to operate than the original version. Flowers overcame the problem of synchronizing the electronics with the message tape by generating a clock signal from the reading of the sprocket holes of the message tape. The speed of operation was thus limited by the mechanics of reading the tape. The tape reader was tested up to 9,700 characters per second before the tape disintegrated, so 5,000 characters a second was settled on as the speed for regular use. The marked Chapter 2 Colossus included the first ever use of what would now be called shift registers, one for each of the 5 channels of the punch tape. There were 5 parallel processing units, each involving up to 100 Boolean operations, although in normal operation fewer channels were examined in most runs. This 5-way parallelism enabled 5 simultaneous tests and counts to be performed for each circuit of the tape. The shift register stored successive bits from each of the tape channels and delivered 5 successive characters to the processors, giving an effective processing speed of 25,000 characters per second. Operation: Colossus used state-of-the-art vacuum tubes, thyrotrons and photomultipliers to optically read a paper tape and then applied programmable logical functions to the bits of the key and ciphertext characters, counting how often the function returned false. Colossus was designed to perform the task of wheel setting, that is, determining the start point of the stream of key characters in relation to the characters of the enciphered message on the paper tape loop. Initially it was only the key wheels that were examined. To keep the size of the task manageable, only 2 bits of the key stream were examined in the first run, then progressively the other bits. Success at this stage allowed the production of a version of the ciphertext from which the key component of the key had been removed, the so-called decay. This transformation allowed manual methods to be used to work out the settings of the cyan mu motor wheels. Later, methods were devised for using Colossus to determine the settings of the SI wheels. All of this required that wheel braking, the discovery of the cam patterns for all the wheels, had been successfully achieved. Later Mark Chapter 2 Colossi were equipped with a special unit to achieve this as well. Programming Colossus was by setting switches and plugging appropriate units together. Sometimes, two or more Colossus computers tried different possibilities simultaneously in what is now called parallel computing, speeding the decoding process by perhaps as much as double the rate of comparison.